Hi everybody, welcome to session number 2 on HDInsight deep dive on the Hadoop cluster type. Today we're going to talk about Hive optimizations. My name is Rasham Gupta and I'm a principal program manager here at Microsoft. And in the last session we covered Hive programming, and today we're going to talk about Hive optimizations. So with that, let's get going. Before we talk about Hive optimizations, let's just understand the two main scenarios for Hive, and then we can do a deep dive on each one of them. So the first scenario that we talk about is called ETL, which stands for extract, transform, load. And the second one is called ad hoc and exploratory, and this is more interactive. So in the ETL, at a high level, the scenario is you take unstructured and semi-structured data like CSV, text, or JSON and XML, and then you run complex jobs to create a cooked data. So these are typically used in production scenarios. The persona here is typically developers. And the way it would work is they pick a dedicated cluster. Typically, it's just a team or a few developers who use it. And their goal is just to make sure that the pipeline runs smoothly. So it's running as a dedicated cluster. The job pattern is programmatic, so you file and forget using an SDK or something like that. The typical job is a full table scan or large joins or long running. So the typical job is you'll take like historic data, merge it with the new incoming data, and create a cooked data in the end. So it's very predictable jobs, but take a long time to run. The problems that customers or developers face here is, how do I run my jobs fast, right? Secondly, what tools do I have to run my jobs programmatically? And finally, what file format should I use to make the jobs run faster? So at this stage, we're going to talk about more optimizations. After the end of the presentation, we will fill the last row, which is the optimizations. So that's the ETL side. The ad hoc or exploratory side, on the other hand, is more for the typical persona here is more BI users or data scientists. So the typical cluster shape is like a shared cluster where multiple users connect. And obviously, that brings the problem of how do you share your cluster effectively so that users are not starved by one user, right? The job pattern here are short-running jobs, and the typical job is ad hoc over refined data, right? And then also the connectivity that users want to use are BI tools. So the problem that customers face here is, how do I effectively share my cluster? How do I optimize my output data for final consumption? How do I connect BI tools? So things like that. So essentially in ETL, the goal is more to run, in ETL scenario, the goal is how to run your job more smoothly and predictably. In ad hoc and exploratory, it's more how do you run your jobs fast and are able to share this with your customers quickly. So now that we understand the two scenarios, let's talk about how we're going to structure this presentation. So we're going to start by learning about where you go to change your Hive settings. Next, we'll talk about the job submission optimizations. So next, we'll talk about the different layers, optimizations in different layers. So we'll start with job submission layer, then we'll go to the execution engine layer, we'll go to the storage optimization layer, we'll go to the file format layer, and we'll end with a summary. So step one, any Hive setting we're going to talk about today, where do you go to change it? So there are two places, actually there are three places you can go to change this, right? And let's talk about all three. Probably the first and the easiest is you can just go to you can change all these settings right in the query prefix. So what do I mean by that? Let me open Putty, and I'm going to log into the cluster. So we're going to log into Hive training batch. So this is my Hadoop cluster. So let me log in. Oh, I entered the wrong username, so I'll have to try it again. So what I'm doing is I'm logging into this cluster, which is the Hadoop cluster, and I'm going to open my Hive shell. In this Hive shell is where I run my HiveQL queries, right? So I'm going to run my HiveQL queries, and essentially at this point, I can just do, if I just do, once the prompt comes, I can type any setting I want and it'll show up. So if I just type set, let me try, I think it's set, it shows me like all the settings of the Hive shell. So almost most of the settings we talk about today, you can just set them right here. So you can say set hive.execution engine equals Tez, and it's going to remember for this session. So again, the easiest way to change any of the settings we're going to talk about today is just going here and typing it on the Hive command line prompt. The pros are it's super easy. The con is it only stays for this session. So if you want to keep it beyond a session, so basically what that means is every time the session is closed and you come back, you will have to retype all these settings. If you want to persist it in sessions, you can go to Ambari. So what you would do is you just go back to your Hive Azure portal, open your cluster. So I open my cluster dashboard, Hive training batch, and right here I will click on this URL, which is my Ambari URL. So when I click there, it's opening. What it's showing me right now is it is showing me the dashboard for my cluster, like the cluster health. Right here, I will click on Hive because that's the service I'm interested in. Under Hive, I'll click on, it's showing me that there are no alerts and the different services that are running. I will click on configurations, and now it will show me all the configurations for Hive that are needed. So right here, I can see at a high level what the different settings are on, what my container size is, how many containers, whether cost-based optimization is on or not, things like that. If I want even more fine-tuned granularity, I can go to advanced configurations, and here I can actually go change any of the configurations I want right here. So like for example, set Hive exec dynamic partition is true, I can change it to false. This will actually store it. Once I save it here and restart Hive, it'll actually make sure that it's persistent across sessions. So this is the second way of doing it. So one way is I can just copy this. I can go back and say set Hive exec partition equal to whatever, true. I don't want to do it, but you get the point. You can change that here. The con is it just persists across session, or you could change it in Ambari. And the great thing about it is it persists across multiple sessions. What this does not do, however, is persist it across cluster restarts. If you want to have it persistent across cluster restart, you actually go change it in the ARM template. So if you search on our documentation, you can find out how to write an ARM template. And while I won't show it here, but in the ARM template, you can change some Hive settings which can stay persistent. So these are the three ways of how you can go ahead and change Hive settings. So now that we've talked about where to go change the settings, now let's talk about the optimizations across each layer. So let's talk about the first one. We've already talked about all of this, how to create a cluster, where to go to change your configurations. Now we're going to talk about the job submission optimization. So let's take a step back and talk about Hadoop 1. So when Hadoop 1 came out, it was built on a very simple concept of like map and reduce, right? And it was optimized for long-running jobs. So very simplistically, a job was submitted, it would acquire resources, some processing would happen, and then the resources would go away. The only problem is all of this was on demand, and so when you would submit a job and to acquire a resource, it would take some time to start up those resources, and then processing. So then the next step of the processing would acquire new resources. So the bottom line is each of these, like each query that you would want to run could take up to 60 seconds to start, right? And it was okay because at that time Hadoop was more suited for ETL scenarios, and a typical MapReduce or a Hadoop job would run for like hours. So 60 seconds, it's not the best place to go optimize for. However, with Hadoop 2, Hadoop 2 brought Yarn, it brought Tez, and it brought this new concept called app masters into the picture. What are app masters? App masters are a concept. So app masters is a new concept, which when you submit a job, it actually is launched in an app master, which can retain containers indefinitely. So the great thing about this is now that it has containers, persistent containers, it eliminates this time of launch or launching new resources, right? So that's the great part about it. The downside is obviously the more containers the AM holds, there is going to be problems with multi-tenancy, right? Because there's going to be problems with multi-tenancy because if you have multiple AMs holding these containers, you actually remove those containers from the resource pool that more customers or users can use. So there's this trade-off of actually using these persistent containers versus keep making sure that you are using it fairly. So what Hive Server 2 did is Hive Server 2 brought this concept of mapping the application master to a query. So what it does is Hive Server 2, every time you launch a new query, it would each SQL query or Hive query would map to one AM, which would map to these containers. So the key point I want to bring about here is if you want to improve your query startup time, you can play with the AM settings and the container settings to make your queries run faster, your first query run faster. So to improve your query startup performance, there are basically three places you can improve your, there are three settings you can change to improve your query startup performance. The first one is the first session startup time takes a while. If you remember when I went back here and I type Hive, let's do that again. When I go here and type Hive, it takes a few good 10 to 20 seconds for it to even launch the session, right? And this is why, so it doesn't matter, look, it's still running. So let's go back to, I just showed a demo, but I think it didn't show up on the screen, so we're going to try again. So if I type, what I did is in my Ubuntu box, I just typed Hive to bring up the Hive shell, and I see it takes about 30 seconds for the Hive prompt to come. Why is it taking 30 seconds? Because it takes those 30 seconds to go create a session. So going back here, if we can decrease the session startup time, you will improve 30 seconds right away, up to 30 seconds to create this session. So that's the first place you can go optimize, right? So because if you're running a BI query and it takes 30 seconds just to start this session, that's really that's not very performant. So the first thing you should do is decrease your session startup time. The next thing you do is when you run your job, the first query takes longer to run since containers are needed to be reserved, right? So so if there's any way you can ask the containers to be pre-warmed, so as soon as your session starts, maybe pre-warm also your containers, that will help. So that, so if you allow container reuse, your containers can be pre-warmed, so that while your session is starting, some containers can also be run right away. And the third thing is, after your query finishes, do not return the containers back to the resource pool, but keep them around for a while. Because typically, if you think about it in BI scenarios, customers come, type a few queries. They typically type multiple queries together in bursts, right? So if you can keep them around, that's one way of keeping them longer. So how do you tune these settings? So again, like I said, there are three different things you can do. Maintain persistent resources so that the test session is faster. The second one is pre-warm your containers, and the third one is disallow complete shutdown. These are the three things you can do to run your first query faster. Now, based on this, you might say, hey, why don't I set my test AM session min held containers to 1,000, right? Basically, what this means is always keep 1,000 containers around. While you can do that, if it's your own cluster, the downside is if you do that for yours, only these 1,000 containers will only be useful for you, and for everybody else, they essentially would not be able to use these containers at all. So that's probably not a good idea. So all I'm trying to say is, while these make sense more, you have to use these wisely. Using a big number for each of these can be a bad idea, because it will ensure that the first user has all the resources and the rest of the users are locked out. However, if you are the only one using the cluster, you can probably set them to a much higher value for each of these to get really good performance. So again, doing these, the benefits are you will avoid the 15+ second startup timer for Hive queries. So what should you set these to? So these are the settings that we talked about. Again, the first 3 are for these test sessions, the next 3 are for pre-warming, and the last one is the for how many containers to hold. So the HDI, we do not turn any of these on. Why? Because we do not know if you want to use your Hadoop cluster for interactive or ETL, but we recommend these settings to you. There's one actually that I do want to talk about, which is the last one, which is test session AM DAG submit timeout seconds. This is set to 300, and we recommend keep increasing it to maybe 600 or more, which basically means keeping it around for 10 minutes. What's the advantage of this is just after your query is finished, you might want to keep the test session around for a little while longer, just if you expect a little bit more, I would say, unpredictable behavior from your users. And so this will just help your queries run faster. So that's the one we would change. By the way, a lot of these settings we've worked with Hortonworks, and a lot of these have also come from their research. So, okay, great. So far we've talked about how to improve your job submission. Next, let's talk about the core engine optimizations. So next, and there are a lot of demos I have, by the way, here, so to help bring that point. So next one we're going to do is look at some join optimizations. So why are we discussing join optimizations? Because in any ETL job, join is pretty much something that's always done. And so we need to make sure that if we understand how joins work, we're able to use them more performantly. So how do join works in Hive? Typically, you have mappers which read input, which are then given to, which then emit a join key value paired to an intermediate file, and then there's a shuffle stage where the sort and merge is actually done, and this shuffle stage is the most expensive. So if there's any way you can actually reduce improve the performance in the shuffle stage, it will give you huge gains. So let's talk about that a little bit more. Before we do that, there are 3 types of main joins in Hadoop, in Hive: shuffle join, map join, and sort merge bucket join. And let's discuss all of them in detail. So the first one is shuffle join. Shuffle join is the default choice, and it always works. How does it work? It reads from one part of the table, and then it buckets and sorts it on the join key, and then it sends each one bucket to each reduce, and then join is done on the reduce side. There is really no setting you need. It works every time, right? But like I said, it's not very performant, but it always works. So I would say this is more the brute force way. The second one is a map join, for which I have a demo, by the way, coming up. How map join works is essentially if you can have one table fit in your memory, then you can use map join. So you read a small table into memory, and you then, so essentially the small table is in the mapper in each mapper, and then that's where the join happens. And then so you don't need a reduce for the join in this particular case. It's very fast but limited, because you need to actually have the table fit into memory. The third one is the sort merge bucket join. So if you have 2 tables which are both sorted and bucketed on the same column, you can do this. This is again very performant. However, obviously you need to make sure that it is sorted and bucketed on the same key. So there is a little bit of overhead. So that said, now let's go to, so the key takeaway here is whenever possible use, if it's a small table involved, use map join. If not, try to use the same sorting and bucketing throughout the different tables that you have, and then use sort merge bucket join. Otherwise, it'll fall back to the shuffle join, which will be slower. Now let's see, how do you tune this map join, right? Like, is there any way to make one fit? Like, how does Hive decide what the memory size is, and how do you, so I'm looking at map join. How do you make sure that you use map join more frequently, right? So we're going to look at our first demo, which is tuning Hive's no conditional task size. And before I run it, sorry, before we talk about it, let me just run it because it takes a few minutes to run. And I want to make sure that, I want to make sure that while we don't waste time. So what I'm going to do is I'm going to just run this job. I'm going to run 2 jobs, okay? And let's talk about the theory while this job is running, and then we can come back and look at what the query times were. So we already discussed the map join optimization. How does it work? An example is select star from a big table and a small table where big table.x equals small table.y. So how does the optimization work? You load the small table into memory and then you distribute it to all the mappers. So we've already talked about the pros and cons. Ideally, the pro is it's much performant, in some cases 10 times performant than shuffle joins. The con is it must fit in RAM. So how can you ensure that it actually fits in RAM? So you can ensure it by firstly turning the setting to true, which is default. By default, it's turned to true, so you don't have to do anything. But the second thing you can do is you can tune the size of the table to cache by setting this setting, right? Now, this setting essentially tells how many bytes of the table can be cached for the smaller table. Now, if you select it to be very high, the queries might fail because your container may not have enough memory. So what I just ran, and we'll go back and check the results. I ran 2 queries. Sorry, I ran 2 queries. In the first query, I said only cache up to 1 byte of the smaller table. So what I'm saying is in this particular case, I'm forcing it to shuffle join because obviously my second table is bigger than the first table. And then I'm running a query. This is actually one of the TPCH queries, which is a standard benchmark query. I believe it's on the 10 GB size. I have 2 tables. One is around 10 GB and one is much smaller. And I'm running these queries. The key thing here is it does a join. And it does a join, and like I said, since I've set the no conditional task size to 1 byte, the small table does not fit into cache. In the second thing, in the second time I run this, I actually set it to be, I believe I've set it to be 500 megs. So I say as long, and I believe this table is like 250 megs, the part table. So I say, hey, as long as in the second query, I say as long as it's under 500 megs, which it is, it says to cache it. And so it will use the map join optimization. So I run these 2 queries and let's see what happens. Let me go back to my screen, and I want to see a couple of things. First, I want to see the map. So this is my first query where I'm running it with the conditional task size of 1, and I run the query. What I see is my query actually has 2 mappers and 2 reducers, right? So that's the first thing I see, and I see it runs in around 30 seconds, right? Now, if I run the same query again by increasing to 500 megs, and now so my part table is stored in 500 megs, I see that it's 2 mappers and 1 reducers. Remember, it was 2 mappers and 2 reducers first. In the original case, right, I see 2 mappers and 2 reducers, and in the second query, where it's actually cached the table, it's only 2 mappers and 1 reducer. Why is there 1 less reducer here? Because the join is actually happening in the mapper stage here, right? And because I also see that the first query took about 30 seconds, this took about 20 seconds. So it's about 50% faster too. So this is an example of how you can tune some settings to force Hive to use the map join optimization. Okay, great. So we talked about the join optimizations. Now let's keep going and talk about the next optimization I have. The next optimization I have is one of the most frequently asked questions is how do I control the number of mappers and reducers in Hive? Again, while we talk about the theory, let me run this query so that this thing can finish and we can come back and look at the results. So in Hive, the way mappers are decided are using something called as splits. So as we know, Hadoop is built around the scale out, divide, and conquer processing, and each file is typically assigned to a split. and these splits are then used in different containers. So the key thing here is the split sizes are tunable, right? And adjusting split sizes may reduce latency. Now, when you run a Hive query, it actually uses its own algorithm to pick the split size, which may or may not be optimal. In most cases it is, but in some cases you might find like in reducing the split size may help with the latency. Again, there is no, it's more like a brute force method which you have to try. So how do you reduce the split size? You actually reduce the split size in MapReduce by using this setting. However, in our clusters, since Tez is the default execution engine, we will just use these settings to tune it. So Tez automatically chooses a split size like I mentioned, but then you can adjust it based on the min size and the max size, and then Tez will pick something. So what Tez would do is, if the setting it picked is lower than the min size, it will choose the min size. If the split size it picked is higher than the split size, it will choose the max size, right? So that's how it works. That's how you can choose the split size to decide to increase the number of mappers, right? So what I'm doing is, in the first case, I picked, I believe this is, one second, let me see, so I picked a min size and a max size, so I think in the first case I picked 524 megs. In the second case I just divided it by 1052 megs. In the third case it's 5 megs. And same thing with max, I think it's 100 megs, and then I just keep dividing by 10. So the key point here, what I'm doing, I'm running 3 queries. The queries are exactly the same, right? So 1, 2, and 3, I'm running 3 queries, they're all the same. All I'm doing is, in the subsequent queries, I'm reducing the min size and the max size by 10. And let's see what happens. So I ran these queries already. The reason I ran them is so we don't waste time waiting for the queries to finish. And what I see is, in the first query, which was about 500 megs, it ran in 22 seconds. In the second one, it dropped to 12 seconds. And in the third one, it dropped to, it pretty much stayed the same. But the key difference here is, I want to go back, look at the number of mappers. It was 120 mappers in the first one. It was 150 mappers in the second one. And it was 210 mappers in the third one. So the key thing is, as I reduced my number of split sizes, the number of mappers increased. In this case, it did have impact on latency in one of the cases, but I mean, this is just a 10 GB data set. So if you had a much bigger data set, you could see a lot more gain in latency. So we looked at how in controlling the number of mappers can improve latency. You can also control the number of reducers, and I'm going to again run this query. Let this query run while we look at the theory. Why would you reduce the number of reducers, and why should it increase latency? So we're going to talk about another optimization soon. It's called ORC. But typically you can use ORC or some other compression to improve performance, right? The only downside is Hive again estimates, if you, let's say original data was 50 gigs and the org with snappy compression made it 1 gig. So Hive will estimate the number of reducers based on a value, a default value of the number of bytes per reducer. So in this case, like 1 GB, it has 256 megs as the default setting for number of bytes per reducer. So even though your original data has 50 gigs worth of data, it compressed it to 1 gig. So Hive will calculate the number of reducers for 4, right? 1 GB by 256 megs, so about 4. Which may or may not be enough, because remember the uncompressed data is about 50 gigs. So in this particular case, if you tune this setting, it might improve performance. So again, I'm going to run 2 queries. In the first query, I am going to run a TPCH query where it uses the default reducer size as 256 megs. In the second one, I'm reducing the default bytes per reducer to be 10 megs. So I expect that the second one will have more reducers than the first one. Why? Because I'm dropping the number of bytes per reducer. And then I expect that because I dropped this, there'll be more reducers, which may result in more parallelism, which may result in increased latency. So let's try that. Let's see the results we got. So this is the query that ran. So in the first case, the query had about 239 reducers, and it ran in about 30 seconds. And then when I decreased the number of bytes, the number of reducers went from 37 to about 1,000. You can see a big increase. And it also decreased the latency from 30 seconds to 20 seconds. Again, a 50% gain, right? So again, just a disclaimer here, the data isn't big, so you're not seeing a much substantial gain, but this is another example where controlling the number of reducers can increase your parallelism. Increase your parallelism and decrease your latency. Okay, the next one is I don't have a demo, but it's basically the cost-based optimization. So using Hive, you can actually do, you can ask Hive to create table-level statistics and column-level statistics, which will allow it to do a lot of cost-based optimizations like advanced rewrites, join elimination, and etc. This is getting better and better, so I highly recommend it to do it. The way to do it is you just do, after you're done building your table, you just say analyze table, customer compute statistics, or you can, and then you can also do it at a column level where you say analyze table, customer compute statistics for columns. So we recommend you doing both because then you will get the best performance. Okay, some more execution engine optimizations, vectorization. So with vectorization, you can improve your performance 3 to 10 times. It today does require org file support, but actually this is a little outdated with 3.5, HDInsight 3.5. You can now also, vectorization also works with text files. The key thing here is, how does vectorization work? Instead of taking one row and doing some operations on it, it takes like 1,024 rows and does operations on it. So it actually is able to do more processing, which results in less, like less function calls and thus improving the performance. The other new thing that was added in recently is Grace hash join. Grace hash join is just, in some cases you may want to choose Grace hash join, which just tells Hive that in case the join that you want to use fails, you can fall back to this Grace hash join. It prevents job failure when hash table size are misestimated, right? So there is a performance penalty, so use it wisely, but in cases where you'd rather have the job run and not care about performance, you might want to use this. Okay, one of the other questions we get is, hey, I have a Thais application manager. What size should I configure it to be? So from our experience, usually even the most complex queries are okay with 4 GB Thais application manager. So while you can control it with this setting, you shouldn't really have to change it to more than 4 GB. So just keep that in mind. So there might still be a reason to do it, but just use it wisely, because in most cases 4 GB of Thais application memory is enough for even the most complex job. However, what's more important with Thais application manager is choosing these Thais AM timeouts. So what are Thais? Let's go back to talking a little bit about Thais AM. Thais AM controls all Thais resources, right? So, and the way it works is once it's idle for a while, it exits. So you can actually control this Thais session. You can keep this Thais session up for a while. So each query you create will create one Thais AM. So one way to keep this session up is to control it with this timeout. And we discussed this earlier, right? One recommendation is don't set this higher than 1 hour, because zombie AMs are still possible, but that's something that is being fixed. But right now, do not set it more than 1 hour. So that's at the session layer. What you also can do is you can choose the min and the max release timeouts for your containers. Why is this important? So if you think about it, when you are, you don't want to exit because your Thais containers are hot and ready to go for performance, right? So if you while you're waiting, you don't want to exit because eventually these containers will be used and you want them to be hot and ready to go. At the same time, you want to exit because you're keeping these away from the pool and giving it away to other people. So What you can do is you can set a minimum and a maximum timeout, and Tez will pick something in the middle. So ideally, so why this is important is just think about it. When you might have a query which has a bunch of mappers and reducers, and the reducers are waiting for the mappers to finish, right? And so what you don't want is if the reducers are idle and they exit before the mappers are finished, then it will take some time to restart these containers or to start them again. And this is where choosing these options wisely will ensure that that those containers are ready to go, right? So the reducers should not exit while your mappers are still running, right? They should be hot and ready to go, and these settings can allow you to do that. Okay, so let's summarize. For the execution option, engine optimizations, you should choose the right join optimization. The default is shuffle join, but you can choose either bucket join or sort merge join based on the options you pick. The no conditional task size is something you can tune. While it's auto-tuned, you can set it to be a little higher, such that you can put in your hash table, like you can put in for map join optimization, you can put in a smaller table there. We recommend it shouldn't be more than 1/3 of your Java's heap size. You can choose the Tez grouping min size and max size for your split size, right? And then you can choose your reducers based on Hive exec reducers bytes per reducer. You can turn the cost-based optimizer stats using this setting. You can choose vectorization using this setting. You can choose hybrid grace using this setting. We recommend to not have your Tezia more than 4 GB. And then finally, we talked a little bit about this, where you can increase your timeout to be about 5 to 10 minutes, but more importantly, configure your container release timeout such that they are not released, so your reducers are still around while your mappers are finishing. Okay, great. So while we're on this, I also wanted to bring about this new feature that we just introduced. We actually introduced a new cluster type called interactive Hive, which uses this concept of LLAP. What is LLAP? LLAP is a new feature introduced by Hortonworks in HTTP 2.5. It stands for long live in process, and it allows you to combine daemons and containers together such that now it can cache, it has in-memory caching, so that it does not have to go to disk every time to read the data. So this is actually very powerful and makes a lot of BI scenarios very easy and useful. So if you think about it, you can, this is an example where now when you run a query, it will print out the number of bytes it hit in the cache or missed. So this is very powerful because now you can, it will try to read as much as it can from the cache. So I'm going to show you a demo now using LLAP. What I'm going to do is I have two clusters. One is my Hadoop batch cluster, and one is my interactive Hive cluster. And I created this table on a 100 GB data set. Again, this is a TPCH query. So it's a 100 GB file in the ORC format, and I created a table on top of it. Why is it ORC? Because today, LLAP only works with ORC format, not with CSV. So that's very important to know. So because of that, you have to make sure that it's in ORC format. So I created this table, and I'm going to run this query using Beeline, which is another authoring tool instead of command shell, and I'm going to run the query at the bottom, both in batch and interactive, and we're going to see if it makes any difference to the performance. So first thing is, let me open the query, the cluster. So what I'm doing is I'm logging into my interactive cluster. By the way, these two clusters are right here. You can see they're both exactly the same. This is using 4 D14 worker nodes, and the other one is also using the interactive Hive cluster, is also using 4 D14 V2s, right? So you can see they're exactly the same configuration wise. And now the font in the green is my interactive cluster, and the font in the orange is my my batch cluster. So what I'm going to do first is I'm going to run beeline in both. What is beeline? We discussed this in our first session. Beeline is a JDBC tool which can connect to Hive server 2, and you can run Hive queries through it. Why are we using beeline? Because it's much lighter to use. Okay, so now I'm going to run this query. So first thing is, let's do show tables on both, just to see that if this table exists. So there is a line item 100 GB arc here. Let's do the show tables. And I see there's a line item 100 GB arc here. Now I'm going to run this query. And the first query in my interactive cluster, so again, the orange one is my batch cluster, the green one is my interactive cluster. The first query in my interactive cluster will run longer. Why will it run longer? Because it's not reading from the cache, but it's reading from the disk, right? Actually, that was pretty fast, in 16 seconds. I want to see if it ran from the cache or the query. It actually read from the cache. So because I had run this query before, you can see it ran it, and it read all the 60, whatever this is, 61 GB maybe, from the cache. And the second one is still running, right? So my interactive one returned in 16 seconds, while my batch one returned in 46 seconds. So that's, if I run this again, it's going to be even faster. But that tells you the power of LLAP, right? So even if the LLAP performance as seen by some of external, these are numbers from Hortonworks and other customers. Hive 2 with LLAP averages 26 times faster than Hive 1 in some cases. So it is substantial gain in performance. Okay, great. So where are we? We talked about where to change the settings, job submission optimizations, engine optimizations. So the next one we're going to talk about is storage optimizations. So one of the basic ones in storage optimization is partitioning. If you're coming from SQL, it's very much similar in Hadoop. Partitioning is done every time you create a partition. A subdirectory is created, which maps. Each subdirectory is mapped to a partition, and one of the common strategy is one partition is per day. So partitioning is great because it allows you to do partition pruning, which basically means you don't have to read the entire table, but you just have to read part of the table. So so it's very important to use partitioning wisely, because if you can do it, you can get drastic gains in performance. So let's go to the next one, compression. So let me actually, okay, so let me run these two queries real quick, and then I will again talk about, just so they run while we are doing. So I'm going to go back to my Hive prompt because I like that better, because it shows me the number of mappers and reducers. So while it's opening, what I'm going to do is, again, I'm waiting for the session to start. Remember the 30-second session timer we talked about? Okay, there you go. So this is running. While this is running, let's talk about what's happening. So I created two tables. One is a line item raw and one is a line item gzip. And the line item raw is just using the raw line item file, which is about, I think, 10 gigs or 100 gigs, I forget. I think this is 100 gigs. And the gzip is using a zipped file. And I'm running the same query, one going to the raw text file and one using the gzip file. Now, based on this, you might think it's great to use gzip because you can compress data to gzip much more and use it. So it's actually not a good idea to use gzip. And why? Let's talk a little bit about the different compression algorithms that you have. These are the different compression algorithms that are available for you to use. Gzip, bzip2, lzip, and snappy. The key thing I want you to look at is the last column here, which is called splittable. What is splittable? Splittable allows you to tell Hive what format to use to whether it can be splittable or not. And gzip is not splittable. So what this means is it cannot do only one mapper, or a few mappers can actually read this file, not many, because it's not splittable. If it's splittable, it'll allow you to read multiple mappers, and it's, as we learned before, the more the mappers in general, the more the parallelism. So gzip is generally not a good idea because it's not splittable. And so you want to, if you really want to use compression, use either bzip2 or LZO if it is indexed. Otherwise, all the other formats are not splittable. So that's the key takeaway, that while compression is good, it's only good if you use the right compression format, which is bzip2. So now let's go back to my demo, and let's go look at the two queries. So the two queries actually ran, and you can see in the first query, you can see the number of mappers was 206, right? And it ran in about 26 seconds. In the second query, where it's using gzip, remember gzip, it's only has 2 mappers. So from 206 mappers, it went down to 2 mappers. And no wonder it's so slow, because there's not enough parallelism, right? So even though Hadoop can support parallelism, we're not using it because we are using a gzip file. Okay, great. Let's keep going. The next one is columnar formats. Why should you use columnar formats? If you think about it, most of the queries you do are based on columns, like group bys and order bys. So columnar formats allow you to store the data contiguously for a column rather than on a per row. So most queries which are done on like group bys and order bys can just read that data much faster. And so columnar formats allow you to make it much faster. So the pro is that your queries can run much faster. The cons is you have to convert your data into these columnar formats. So so it only makes sense if you're going to use this multiple times, right? If you're going to just query it once, makes no sense because you're going to pay the cost of converting it. But if it's like a table which will be used by many data scientists or again and again, it might make sense to do it. There are 2 ways to do columnar format options: org file and Parquet. Org file is best in Hive. It allows you to do vectorized execution, and it also allows you to do ACID, which is insert, update, and delete. Parquet is fully supported also. However, there is no vectorization or ACID. But Parquet it works great if you have mixed Hive Spark workloads. So the key takeaway here is if you are using if you're only planning to use Hive, stay with org because it gives you much more optimizations. But if you're planning to use it across like different workloads like Spark, use Parquet. You can do a few more org set tunings. You can do you can choose different compression types like zlib and snappy. It depends on whether you want to pay the cost of performance. You can also choose the stripe size, and especially if you have to store large fields like blobs or XML documents, we recommend increasing the stripe size. And finally, you can also do Bloom filters, which accelerate highly selective queries, and you can do that using this option. Okay, let's talk about JSON. Because why are we talking about JSON? Because this is another common format that customers have, and the conversation is worth having because you should know what type of JSON to use, like UDF to use. So after CSV, the most popular input format is JSON, and there are multiple options to parse JSON. You can use the Hive built-in UDFs like getJSON object and getJSON tuple. However, as we will soon discuss, these are not the 2 best choices. So what customers use are like the custom Serde and OpenX. And we actually looked at that in our previous recording about how to do Hive programming. I showed you how to use it. So if you want to also see how I actually used it in action in a demo, we can go back and refer to that setting. So how does this work? Like I mentioned, there are the first 2 getJSON object and getJSON tuple are available out of box in Hive, but the third one you have to install. So let's look at each one of these and decide whether that will be what the pros and cons are. So for getJSON object, it's flexible as its schema on read. However, it's not very performant and it cannot handle arrays. So if you have a very simple JSON with no nesting, also if you want to do it more at like you want to do it ad hoc, you should use getJSON object. For something which has more nesting, you can use getJSON tuple, It is more performant, but it is very clunky, and you'll have to write a lot of multiple lateral views, right? So these are the two that's available. I do not recommend using either. Instead, I recommend using this third-party OpenXSurday, which is very flexible. It works with complex JSONs. However, you will need to install it, and I have a demo of how to do it in a prior session. So key takeaways: use the OpenXSurday for more complex JSONs. Okay. So what are the key storage formats optimizations? Always partition your data. When you do use compression, use bzip2 or LZO, and you can use arc. And when you like columnar format, use arc. I don't know what happened to my colors here, but columnar formats use arc for Hive and arc for Parquet for more mixed workload scenario. And you can use different arc settings for even further gains. And finally, when you are using JSON, you can use the Hive built-in UDFs for simple JSONs, but for complex one, use the OpenXSurday. Okay, we're now in our final section of optimizing Hive, which is file formats. So I briefly touched about this briefly, but I will talk about this again. One of the key differences between on-prem and cloud Hadoop is that we decouple storage and compute. And this is one of the great things, because you can now scale out your storage separately than scaling out your compute. So we hear this a lot from our on-prem customers, that they start with, let's say, a 100-node cluster. And while their jobs are not running 100-node cluster, they're not using the resources of all the 100 nodes in terms of like compute. They are running out of disk space. So what do? Then they put in another 50 nodes, and just to increase the storage. With cloud, you don't have that problem, because we use like Azure Blob Storage or Azure Data Lake Store. That's actually much cheaper, and also you can scale it indefinitely, and that's independent of what you have on the compute side, right? So that's one of the great things about it. However, the downside is there is cloud storage limits, especially for Azure storage, right? And let me tell you what I mean by that. So each Azure storage account has a per file throughput, and it also has a per account throughput. So one of our customers, what they wanted to do is they wanted to partition data on year, month, and day, right? So they looked at the data, they created partitioning based on the year, month, and day. The problem was, once they created these partitions, simultaneously read-write caused I/O bottleneck. Why did it cause I/O bottleneck? Because reading it simultaneously exceeded the throughput by Azure storage, right? So what we went and said is, okay, one way to do it is use multiple storage accounts. So they used storage account 1. So in the prior example, they just had one storage account, right? All of this is one storage account. In the subsequent step, they created 3 storage accounts, 1, 2, and 3. And they put all the partitions of 1 month and year under one storage account, under second storage account, and a third storage account. And now when they tried to do simultaneous read-write, they were expecting to see an improvement in performance, but they didn't. The reason being, there were multiple mappers here all trying to read from the same storage account, and that's a problem too, right? Because why? Because like I said, the Azure Blob Storage creates throughput on a per account basis. So what they went ahead and did is they now created multiple storage accounts, but more importantly, the partition for each month and year was not put in the same storage account, but sharded across different storage accounts. So while this worked, you can see this is pretty painful, and also this needs to be changed more at the compute, like in your Hive query, you need to go change this. So we actually went ahead and introduced Azure Data Lake Store, which does that for you. So you don't need to go ahead and do all this. It is much higher cloud store limits. So there are no limits on file sizes. It's optimized for throughput. It's optimized for IoT. So we highly recommend using Azure Data Lake Store. So the summary here is the file system that you should use as HDFS should be Azure Data Lake Store instead of Azure Blob. Okay, so that brings us to the summary slide. We started with this slide is what optimization should be used for the two scenarios, ETL or ad hoc, and let's talk about those again. So for ETL, you should use partitioning, you should use cost-based optimizations. For large joins, you should always, you might want to increase your taste container size, use map join or sort merge when possible. You should tweak the reducers, you should use org file, and use ADLS. If you are using compression, use bzip2. For ad hoc and exploratory, use LLAP because it uses in-memory. Also, for LLAP to really work, you must use org. You should choose ideally a different cluster than batch jobs. We discussed a lot on session startup times. You should invest in session startup times and pre-warming containers. So hopefully that made sense. I know it was a lot of settings, but hopefully these settings should help you build your ETL and exploratory pipelines much better. And if you have any more insights, or if you need any more insights or want to learn more about HDInsight, go search for the HDInsight online or read our documentation or reach out to us on our forums. Thank you very much, and I look forward to connecting with you in a future session.